Well, welcome to 8.2 Part B lecture. In 8.2 Part A, we learned how to graph trigonometric function of tangent, as well as how to graph transformations of the tangent function. And we also learned the basics of secant and cosecant. So in this last part, we're gonna look at graphing transformations of secant and cosecant, and we'll also look at graphing the cotangent function. So let's go ahead and get going. Okay, so graphing a variation of cosecant. And I probably should have added this in when we started graphing transformations of the tangent function, but it didn't really dawn on me until I started looking at this problem in detail that there's a step in their how to feature box right there that I feel is missing from the process of graphing both secant, cosecant, tangent, cotangent, and even sine and cosine transformations. So I'm actually going to start by inputting another step in here for you. And I think that this will demystify and make this process a little bit easier. So between step 4 and 5, I'm going to add a step that says identify five key points. Okay, so to do this, if you remember correctly from all of the trig functions that we've already looked at graphing, there are basically 5 areas of concern. We have, especially with tangent, well, actually all of them. We're going to have vertical boundaries, and in tangent and secant, cosecant, and cotangent, these are actually vertical asymptotes that show up. And we know that these also follow key points of sine and cosine function as well. They're just not asymptotes at this point. They're the beginning and the end of the period, which we know in its parent form, the sine function begins at the origin, it moves up and then down across the x-axis and dips down and then comes back up and ends at the x-axis in its parent form. And that entire period goes from 0 to 2 pi. And well, let me actually just give a quick sketch here so that this will make sense. So let's pretend that this is the graph of sine. We have our x-axis here. And this is 2 pi. So right halfway between would be the pi mark, and then halfway between that would be pi over 2, and then halfway between pi and 2 pi is 3 pi over 2. Okay, so if I came in and just gave a basic sketch, we also have upper and lower boundaries at 1 and -1. And we've already discussed this in a lot of detail, so I'm not going to go too deeply into that. All right, so we start at the origin. We know it goes up first to 1, and that hits at pi over 2, halfway between the beginning and the halfway mark. At the halfway mark, it's going to hit right on the x-axis, then it's going to drop down at that second halfway mark between pi and 2 pi, and then end back up at the x-axis. So it looks kind of like this. Cosine differs slightly. Let me get a different color just to remind you. Cosine starts at the top and it coasts down, remember? So cosine coasts down and it actually crosses the x-axis at the pi over 2. It's going to bottom out at pi. Well, that should be going lower, down to 1, negative 1. It's going to come back up through and cross the x-axis at 3 pi over 2, and then it's going to end at 1 at 2 pi. So these are the 5 key points that I am talking about in this intermittent step between 4 and 5 and how-to feature. So you can see we have this period from 0 to 2 pi for the sine and the cosine function. Halfway between 0 and 2 pi is pi, and that's going to be either your, it's going to be an x-intercept if we're talking about the sine function, or it is going to have an output of negative 1. It's going to be at the bottom of the valley there for cosine function. And then we have these other 2 halfway marks between there, which give us other key points of these functions. So notice that this makes 4 little intervals. These 5 x values of 0, pi over 2, pi, 3 pi over 2, and 2 pi give us 4 intervals that are very important in shaping these functions. So we're going to find these 5 key x values. And so I could really say, instead of saying key points, we could say key x values that give us those boundaries to start shaping these functions for us. We know what the secant function looks like, you know, normally without being transformed. Let me go grab a picture of that. I'm going to pause the recording. Okay, so I went out to Google Images and found an image of the secant function. I don't have it on my whiteboard anymore since I started with Part B, but let me just show you how those same key points or key x values show up in these functions. Well, not the same exact ones, but you have 5 key points, key x values that can help you shape your function. Okay, so let me grab my pen again. So for the secant function, I have a key x value at negative pi over 2. I have a key x value at 0, at pi over 2, at pi, and at 3 pi over 2. So what's going on at negative pi over 2? I have an asymptote. What's going on at 0? I have a valley, bottom of a valley, so my vertex there. Pi over 2, I have another asymptote. Pi, I have another vertex, top of the mountain there, so a maximum. And then finally, 3 pi over 2, I have another asymptote. So if we can successfully identify these x values that are going to be boundary marks for us, then we know what the shape of the function is going to look like. Secant in its parent form, where it has not been reflected, is going to open upward first, and then so it's an open U shape, opening upward, starting at negative pi over 2 and going to pi over 2, and then I have the reflection of that across the x-axis. So let's go ahead and move forward with finding the necessary information that we need to graph. Let's see if I can actually clean off this without cleaning off my writing. Oh yeah, I need to write how we're going to find those key points as well. And I'm going to take that off there too. Okay. So, because we know the period is the very beginning, and or the beginning of our period is one of those key points we're looking for, and the end of our period is another key point we're looking for, what we can do to begin identifying those 5x values is take our period and divide it by 4. Remember, there were those 4 sections to it. And what that does is it gives us the amount to add to the last key x value. Let's change that. Key x value to get the next one. Okay, so I think this will make a little bit more sense when we see it worked out. Okay, so our first step is to express the function in its full state, a times the secant of b times x minus c plus d. So just identifying those different values, a, b, c, and d. My a is -6, b is 4, c is 2, and d is -8. Now, that d value, in my opinion, is the easiest and the first thing that I usually go for when I'm graphing these transformed functions. So remember, the d value tells us how far up or down we have shifted. So what we have here is a d value of -8. That's going to be our new midline. So I'm going to go ahead. Now this graph, I should have given different increments on this graph here, at least with the y-axis. But if you notice, it's actually counting in 2.5. So -8 is going to be a little bit below that line, that grid mark right above -10. That's about -8 right there. So I'm just marking my midline. I'll also note the equation of my midline is y equals -8. Remember, when we write it as an equation, it's always going to be y equals some value because it's a horizontal line. All right, the next easiest thing is to decide, okay, how far above and below that midline is my cosine going to move? Because remember, we use the cosine to graph the secant because it's the reciprocal function of the secant. I'm sorry, of the cosine. The secant is. Okay, so if I look at my a value, the absolute value of a gives me my stretch factor, which if I'm dealing with sine or cosine gives me my amplitude, but this particular type of graph doesn't have an amplitude because it's not that wave that's modulating up and down. It's the reciprocal of that. So the absolute value of a in this case is the absolute value of -6, which is 6. Now, this is the amplitude of my cosine function that I'm going to use to base how I graph my secant function off of. So I need to go 6 above and 6 below my midline to see where my cosine function is living. All right, so 6 above 8 puts me at -2, so that's right above this first grid mark below the x-axis because that grid mark actually stands for negative 2.5. So I'm just putting it right above there to represent negative 2, because from negative 2 to negative 8 is 6. And I got that 6 from up here. And then negative 8 and 6 more down takes me to negative 14, which is about right here. Whoa, sorry for the waviness there. This is supposed to be a horizontal line. Use your imagination on that. Okay, so I'll just label these out to the side here. This is negative 2, and this is negative 6 there. So recall my cosine's gonna coast between those, and then I base my secant off of the graphing my cosine. That's going to give me some key points that I need. Okay, so let's identify the period of the function. Let me change colors. And you can see the period is identified by doing 2 pi divided by the absolute value of b. So my period is 2 pi divided by the absolute value of 4, which is 2 pi over 4, or pi over 2. And just so you know, that's approximately 1.57. Just to give you kind of an idea of where all this lives. All right. And since I translated that, and I'm going to be looking for those key x values, I'm going to go ahead and translate everything that's written in pi form on the x-axis into its decimal equivalent. So pi over 8, you're looking at approximately 0.39. I'll just put it above the axis here, 0.39. Pi over 4 is approximately 0.79. And of course we have 0 here. And I'll fill in a couple more as we move forward in this problem here. Okay, so the next thing to do is to identify the phase shift. So phase shift is given by the ratio C to B. So phase shift is given by C divided by B. And in this case, my C value is negative 2, not positive 2. That's plus 2, so that's really minus negative 2. I almost didn't catch that. Negative 2 over 4, which is negative 1/2. So everything's gonna shift negative 1/2. All right. So let's start with the graph of the cosine function here. Let me get a different color. Okay, so the cosine that's weaving between those boundaries that the absolute value of A gave us is y equals negative 6 cosine of 4x plus 2 minus 8. And we will go ahead and find our 5 key x values here. That's going to tell us where our period begins, where it ends, and those five vertical lines that are either boundaries or asymptotes or point to key points in the function itself. Okay, so we are identifying, let me get another color here. We are identifying our 5 key X values. Okay, so first we want to take our period and divide it by 4. Our period is pi over 2. I got that right up here at the top. And I'm going to divide that by 4 because I know I have those 4 sections that were created by the 5 boundary lines. So pi over 2 times the reciprocal 1/4 gives me pi over 8. Okay? All right, so my first key X value, X sub 1. Notice I shifted everything. The cosine function starts at 0, 1, but I'm shifting everything left 1/2. So my first key X value is negative 1/2. And now this information right there, the pi over 8, that tells me I'm going to get a key vertical boundary line every pi over 8 after negative 1/2. So my next key value is negative 1/2 plus pi over 8. And I have to find a common denominator to add those together. So I multiply, I don't have room to show all this, but I multiply that first fraction by 4 over 4, and I end up getting negative 4 plus 2 pi divided by 8. And when I put that into my calculator, I get that that's approximately 0.29. And obviously this is equal to negative 0.5. Okay? My third, I take my second one, negative 4 plus 2 pi over 8, and I add my pi over 8 to it. And when I add those together, I end up getting negative 4. I'm sorry, that first one was pi. My eyes went crossed there. This one's 2 pi. Okay, so negative 4 plus 2 pi over 8. And that is approximately, my eyes went really crossed. This one's 0.29. Sorry about that. This one's actually negative 0.107, approximately. My fourth key point, when I add negative 4 plus 2 pi over 8 to pi over 8, I get negative 4 plus 3 pi over 8. And that is approximately 0.68. And then finally, X sub 5, have negative 4 plus 3 pi over 8 plus pi over 8 gives me negative 4 plus 4 pi over 8, which is approximately 1.07. Okay, so that's why I started putting decimal equivalents on my graph here. So, I have, let me go back and point out some more values for you. Halfway between 0 and 0.39, right here, this is about 0.19. And then halfway between that is about 0.095. And negative 1/2 is roughly, very roughly, right between negative pi over 8 and negative pi over 4. So this is just about negative 1/2. And okay, so pi over 8 is 0.39, so this is negative 0.39. And I'm needing negative 0.107. That's about right here. Negative 0.107. Okay, and then I got 0.29 is about right here. This is about 0.29. Then I've got my 0.39 right at pi over 8. And halfway between 0.39 and 0.79, right halfway between pi over 8 and pi over 4, I've got approximately 0.585. Okay, so in actuality, this one right here is a little further towards the x-axis than I have it drawn here. But you know, we're graphing by hand, so close is good enough here. All right. So why do we need to know where all of these key points or key x values are? It's so that we can start crafting that cosine function that gives us the reciprocal secant function that we craft that off of. So I'll just put arrows, or actually I'll go ahead and put boundary marks where that the cosine's going to, I'll just point them out to you. So we have negative 1/2. So this is where my cosine's going to start. It's my starting point. Remember, I shifted 1/2. Right up here, we discovered that. And my next point is halfway between, so the negative 0.107 right here. That's going to be where it crosses my midline at y equals -8, the cosine function. And then I have my next one at 0.29. Then I have 0.68, which is about right here, actually. I didn't mark it. It's about halfway between 0.585 and 0.79. And then my other one's off the graph, but you really don't need it, and I'll show you why. Okay, so remember, cosine starts in its parent form. It starts at 0, 1, and it coasts down. But notice this A value is negative, so I have the reflection. So my cosine actually starts at the bottom and goes up. At my next key x value, it's going to go through the center, and then it's going to peak out right in the middle, and it's going to come back to the midline, and then it's going to go down somewhere out in here. Like I said, it's off the graph. It's at an x value of 1.07. So here's what that looks like. I come up. It's a very wide-looking cosine function. Okay, so there's kind of my cosine. Why in the heck did I spend so much time doing that? Because we know where the cosine in its parent form crosses the x-axis, which in this case is y equals -8. That's my midline. So where my cosine crosses my midline is where I'm going to have asymptotes for my secant. So I have an asymptote going through -0.107, and I have an asymptote going through 0.68. My secant function is based on my cosine function. This is going to be the bottom of my valley. It's going to be my minimum, and my cosine's going to, my secant's going to come up and open up into that U shape. Use your imagination once again. My pad's slippery, obviously. That looks terrible. Use your imagination. But that's how you hand graph the secant function transformed. And I think even though it took us a while to get through this one example, now that you know what those key x values are and how to get them, it makes graphing the transformations of the other trig functions so much easier. So let's go ahead and take a look at graphing a transformed cosecant function. Okay, so don't forget the cosecant is the reciprocal function for sine. So instead of focusing on cosine, we're going to focus on that sine wave riding through there. So first things first, and don't forget our extra step in here, our key x values, our 5 key x values, and we get that amount to add on to each of them by dividing the period by 4. So first let's identify our A, B, C, and D. A is 2, B is pi over 2, C is 0, and D is 1. Let's get the easy stuff out of the way. Our midline. My midline's at 1. Absolute value of A is absolute value of 2, which is 2. So I'm going to give guides 2 above my midline. These are the lines that my sine wave's going to travel through, and 2 below. So up to 3 and down to -1. Okay? Let's check our period here. So my period is equal to 2 pi divided by the absolute value of B, which is 2 pi divided by absolute value of B is pi over 2. So that's 2 pi over understood 1 times the reciprocal 2 over pi. My pi's divide out, and I get a period of 4. Okay, my phase shift. My phase shift is C over B. That's 0 over pi over 2, which is just 0. In other words, I haven't shifted left or right horizontally at all. So actually, I've got some really nice values to work with here. Because I haven't shifted left or right at all, I know that my sine wave starts right there at, well, if it's in its parent form, at the origin, but it's on the y-axis. So since it's my midline, my sine function would start right there at 0, 1. So I've got a boundary here. That's my sine wave point that I have there. And remember, it moves up and then down and up. Okay, so I know I have a period of 4, so I can go ahead and give my other ending boundary. All right. Let's go ahead and find our key x values. Well, since I didn't shift left or right any, my first x value is going to start at 0. I need to do the period divided by 4 to know how much I need to tack on to each of the previous x values to get to the next boundary. So my period's 4. I divide by 4. I'm only going to increase by 1. Easy math here. My next key x value is 1. My third key x value is 2. My fourth is 3. And my fifth, which we already have boundaries drawn for, is 4. Okay, so I'm just going to go and put my other key boundaries in there. 1, 2, 3, and 4. My sine wave starts on the y-axis because I have not shifted left or right any. I move up first because it has not been reflected. I come back down and hit my midline, move down and hit my low boundary, move back up to my midline. This is my sine wave. And I base my cosecant graph on this sine wave. So what we learn is that wherever my sine wave hits my midline, that's where I'm going to have asymptotes for my cosecant. So I have an asymptote here, an asymptote here, and an asymptote here. And my cosecant, I have a maximum at my sine wave, so this opens upward. I have a minimum at my sine wave here at 3, and that opens downward. That's it. Easy enough, huh? So wasn't it good that I painfully took you through that first example there, because that one made this one feel nice and neat and easy. Let's go ahead and take a look at the cotangent function. So we'll look at the cotangent function in its parent form, and then we will work on a transformed cotangent function. Okay, so first thing I want to point out to you is that the cotangent is the reciprocal tangent, but the tangent, remember, is sine over cosine. And when you do your fractional math, that comes out to mean that the cotangent is the cosine over the sine. Just a reciprocal. All right. So I have the chart here filled out for us. This just comes from our unit circle. And I even put the cosine over the sine here so that we can just do the division downwards and write our result here in that block there. And I've already figured all of these for you. But you can practice your fractional math and go back and work with these a little bit. But for the sake of time, I'll just fill these values in. 1 divided by 0 is undefined. So we're obviously going to have an asymptote there. Square root of 3 over 2 divided by 1/2 ends up being the square root of 3. Square root of 2 over 2 divided by square root of 2 over 2 is 1. Nice and neat. 1/2 divided by square root 3 over 2 is square root 3 over 3. 0 divided by 1 is 0. Negative 1/2 divided by square root 3 over 2 is negative square root 3 over 3. Negative square root 2 over 2 divided by square root 2 over 2 is negative 1. Negative square root 3 over 2 divided by 1/2 is negative square root 3, and negative 1 divided by 0 is undefined. Another asymptote. So, in its parent form, the cotangent function has asymptotes at an x value of 0 and an x value of pi. So its period is pi. So I have an asymptote at 0, x value of 0, and pi. So that's just one period of it. I could continue. I could go through another period, and that would be at 2 pi. Every one period, we're going to have another period of the cotangent function. All right. So let's put some easy key points on here. We have pi over 4, 1 is pretty easy. Halfway between 0 and pi over 2 is pi over 4. Now these are counting in 5, so it's barely off of the x-axis there. Once again, not the best choice, Libby, in scaling my axes here. Okay, and then we have pi over 2 and 0. That's pretty easy right here. And then we have 3 pi over 4 and negative 1. 3 pi over 4 is halfway between pi over 2 and pi, and that's in negative 1. Okay, pi over 6, if we want to get fancier, pi over 6 and square root of 3, let's see, if I go to my calculator, the square root of 3 is equal to 1.73, so it's a little higher than that one. And pi over 6 is somewhere around in here, so it's going up a little bit, and it's going down a little bit here. So it looks a lot like the tangent function, just reversed. So I start increasing into positive infinity towards the left asymptote, and then decreasing into negative infinity towards the right asymptote. So I can just mark my center with all of these and just, you know, sketch what my cotangent function is going to look like. Sorry for the shaky hands. I've had a lot of coffee today. And we could keep on going with that. All right, finally, let's look at a transformed cotangent function. Okay, we're going to add the stuff in there to find your key points. Remember, period over 4 tells you how to increase there. Okay, so identify our A, B, C, and D. A is 4. B is pi over 8. C is pi over 2. And D is negative 2. All right. So, our easiest thing first, our midline. Negative 2. Ugh, this is even worse. These are counting in, let's see, they're counting in 2.5s again. So it's between the x-axis and that first grid mark down. I apologize that I wasn't more careful. And I'll label this. Okay, so this is that midline, y equals negative 2. And then I have my upper and my lower boundaries that tell me where key points are. So absolute value of A is absolute value of 4, which is 4. So 4 above and 4 below that midline. 4 above the midline puts me at 2, so not quite at that first grid mark. And 4 below puts me at -6. About right here. Okay. So my period is equal to 2 pi. I'm sorry, it's equal to pi, period of pi, divided by the absolute value of b. So pi divided by pi over 8 gives me a period of 8. When I do my fractioning math there by multiplying by the reciprocal, my pi's divide out. My phase shift. Is C, which is pi over 2, divided by B, which is pi over 8, which is the same thing as pi over 2 times 8 over pi. Those divide out. 8 divided by 2 is 4. So I have a period of, a phase shift of 4. Positive. So what that tells me is instead of my cotangent function starting with that asymptote at 0, that's going to shift it to the right 4. So my first asymptote and my first key x value is at 4. Okay? And let's see what we need to add to each of those key x values to get to the next one. So for my key x's, I do my period divided by 4. My period is 8, and I divide that by 4 and get 2. So I'm going to be adding 2 to the previous key x value. My first key x value is 4 because I had that phase shift of positive 4. My second one is 4 plus 2, which is 6. My third one is 6 plus 2, which is 8. And my fourth one is 8 plus 2, which is 10. And finally, my fifth one is 10 plus 2, which is 12. Okay, so I'm just going to go mark those boundaries for myself. So I've got one at 6. I've got one at 8. Got one at 10. And got one at 12. Okay, so let's look back here. I had that x-intercept, or my midline intercept, if you will, was it was in the very center between 0 and pi. So between the period, right at the very center, the midpoint of the period is my midline intercept. And then halfway between my midpoint and my leftmost boundary, asymptote, was my next key point. And then halfway between was another key point. So I use my upper and lower boundaries that I found using the absolute value of A to show me where those key points live with my graph. All right, so I know that in the very center between my asymptotes, so let me actually make my asymptotes different colors. So I have an asymptote here and an asymptote here. All right, so in the middle, on my midline intercept is right in the center. And then my next key point, I have not reflected, so I move up towards the left asymptote. It's right there at that upper boundary given to me by the absolute value of A on my second key X value. And on my fourth key X value, I'm at that lower boundary given to me by the absolute value of A. So this looks like this. It comes down, and it snakes across, and then moves down to negative infinity. That's all I have for you for 8.2. I hope that this part B was helpful for you, and we will soon look at 8.3 together.